what we're going to be going over here is looking at a determinant here, and we're going to look at this determinant in terms of gradients or changes in slopes here. And we'll also be looking heavily here at the visual perspective of our determinant. Okay, so our determinant that we're going to be looking at here is going to be based on the production function, which is really similar to the Cobb-Douglas production function. Okay, so this is what we're going to be dealing with here. Just understand where our determinant is going to come from. Our function here is going to be some revenue output here, so we're going to have some unit price here on a product we're selling, and we take that times some material and labor inputs here raised to some exponential or fractional amounts. And then we'd subtract from it the unit price here for material and labor based on some cost constraint. Okay, so that's what we're dealing with here. So we're going to set up a 3x3 matrix here, which is going to really be the sum of products here on the second partial derivatives here of this production function. Okay, so what we would do here is we would set up, it's really called a Hessian matrix here. But the only point is here, when we set up this matrix, I want to point out that it's going to be really a multivariate calculus type problem here that we're going to be looking at. And really these numbers here, or these algebraic terms here in this matrix, really are the second partial derivatives of our production function here. And we do that in terms of material and labor. So the only point is, what we're showing here is you're going to have material raised to some exponential amount here in the numerator times some scalar amount here, and then it'll be divided by labor raised to some exponential amount as well here, and so on here. So that's how our second partial derivatives are going to be here. And really these deal with the change in slope here, or a change in slope in terms of a determinant. So what we do here, we just go and solve this matrix here. Well, you're not going to do this by hand. This is where you're going to do some computer solution here. So I use MapleSoft here. So if we solve this 3x3 matrix here that we've set up on these second partial derivatives, we're going to come up with some multivariate determinant solution here. And it's really a three-part solution: 1, 2, and 3. And we're just expanding on our multivariate problem here for labor and material raised to some exponential amounts sitting in numerators and denominators and so forth. Okay, so really this is what this we're going to be looking at here. We're going to be looking at this three-part solution here, this algebraic solution, or the multivariate determinant solution, and we're going to look at it in terms of the gradient. Okay, but just understand what we're doing with determinants here. Now, normally what you would do for a determinant, you're going to be looking at a block of numbers. In this case, it would be that 3x3 matrix built off our second partial derivatives here that we set up. And they just be a block of numbers here. And that would be based on just some solution point. You'd have a certain amount of material and labor. In this case, what we'll just look at here is our labor input was 78 point some units, material 69 point some units. Put it into our determinant algebraic solution, you come up with the determinant matrix, or block of numbers, and then you would further go and you'd solve this determinant matrix here, this 3x3 matrix, and you're going to come up with a single number here, which represents the volume, or the change here in our slope, or the change that we're looking at with this determinant here. So that's what we'd be doing. We're going to be dealing with the algebraic solution here and understanding a little better through pictorial graphs here of that solution, or plots. And just to understand here further, just remember, we would have, with this portion here, this would have been a linearized, our determinant here, that 3x3 matrix here, and really what it's composed of is some row element here, a vector representing a row element, then another vector here is looking, that would be like the first row, then the second row here has another vector representing it, and then the third row here has a third vector here. So really this determinant, the 3x3 matrix here, is related to our, obviously, it's based on our determinant here, the algebraic solution. Anyway, the one down here is really a linearized, or that's our determinant matrix here. And it's all based off this production function. I'm showing this production function here. This is a function here that we started out with a certain revenue per unit, and then material and labor inputs, and then we subtract out the cost here, material and labor here. But we've done this, and we've taken second partial derivatives of that function to looking at the change in slope. I'm just showing this change in slope here. And really, we'd be looking at three different outputs that we'd be looking for this problem that we're looking at, just for demonstration purposes. Okay, so let's go up here, and let's look at what we're talking about. Okay, remember our multivariate determinant here, that three-part solution here. We have 3 rows, 3 columns here, so we have 3 different algebraic terms here, or that determinant would really be the sum of products of that 3 by 3 matrix here. And you can look at it in terms of volume here and gradients, or we're going to look at it in terms of gradients here, where that's the direction here of your maximum output or minimum cost in this case. And it's a path that we'd be looking at here. And we're also going to be looking at the gradient field. And just for the numbers that I'm showing here, we're going to be looking at those numbers. We had 69.6 units of material here and 78 units here of labor that we put into this production function here. It's based on that production function. But what we do here, I'm using those units of material and labor here that we put into our multivariate solution, that 3-part solution here. And what we want to look at here, I'm going to have these color coded here. I'm going to call this first volume here, that first sum of our products here, we'll color code that red. And this is the key here. Those numbers that we put in here, that if I put at 69 units of material, 78 units of labor to their fractional amounts, I'm going to come up with a volume here based on our determinant solution. It's 201,600. That's the volume here. And then if I move over to what I've color-coded blue here, the second sum of our products here for our determinant, it's going to be 194,200 based on those units that I'm looking at here for material and labor, that's 69 and 78 and so forth. And then looking at our third part of our sum of products here, we'd have, I've got that color coded. This one, the blue one, 194,200. Now this green one here is 97,220. Okay, so the only point I'm looking at here, and we'll look at those in terms of our gradient. If I would sum my red portion here plus my blue portion plus my green portion, the volumes here, I'm going to come up with the sum total here is going to be it's 4.973 10 to the 5th, 497,300. Just looking at the our sum of products 1, 2, and 3 here. And that is really the solution. If we went in and we did our determinant, that was our solution that we looked at with those block of numbers here. That's what we're looking at. Just understand it. So that's one of the key points I want to make here is we have those 3 by 3 matrix here, 3 rows, 3 columns here, and then going and solving it. In this case, it's really to deal with slopes of the second derivative here, or change in curvature in our slope here. But I just want to understand how we got to where we did here and how you can really look at it and track and look at how you come up with that determinant. If you come up with that, looking at that block of numbers, we would have come up with this number here, but then it's broken apart between our sum of products between 1, 2, and 3, those 3 by 3 matrix or rows in our columns here. Okay, so that's how what we're going to be looking at here. But let's go and let's expand on this multivariate determinant, our solution here. So what I've done here, looking at it, this blue surface here, that's actually, and I've got it graphed out here. You can see it's sort of a checkerboard here, plot out here, where that is taking our determinant, our 3-part determinant here, sum of products, and just summing it or plotting it over some range here. Material and labor, I'm going, I guess my labor here would have been 0 to 250 units, and material here, I'm showing as X here, 0 to 250 units here. So you're going to have some shape to this 3 by 3 sum of products here. But what we want to look at here, we want to break this apart, and we want to look at the determinant or the gradient field, which is really the change of slope here. So what I've done here is I've done a gradient against that 3-part solution here, our sum of products, and this is the way I broke it down here. And I'm showing it with these arrows here. This is all generated here with the MapleSoft computer gradient function here. So what you're going to start here when we have our initial inputs here, first looking at the red portion, that was that 200, that was our algebraic part here to the first part of our determinant solution here. You can see labor raised to some exponential amount here, and then material, that's in the numerator, material in the denominator. And the same for the other 2 parts here. So looking at our red portion here, they're kind of overlapping here, but first off, let's look at this, what I've got shown here, this blue deal. That's actually taking this function here and just plotting it against the maximum output in this case, or the minimum cost here that we'd be looking at for this determinant function. That I've done with MapleSoft here, and I identified a couple points here that we'd be looking at here, those yellow spheres here. But this gradient path, that's what we're looking at. And this determinant here, that's blue portion here, that is what I've graphed out here. The three-part solution, just graphing it out or plotting it out all at the same time, based on material and labor, or in this case I put X and Y inputs here. Okay, so you can see what's going on. You start out here with a real steep slope, and then we're looking into it here, but it starts leveling off. A little hard to see here. But nonetheless, what I wanted to do here is this determinant we have has this gradient field, and getting back to that. So I got my red arrows here, and these arrows are pointing in the direction here of our greatest increase or a maximum output for that production function that we were looking at here. So really we're looking at it. This red one here is a little smaller here, and as we move here across our function, increasing our material outputs here, increasing our units of material here, you get bigger and bigger arrows here saying we're greater and greater output here based on our gradient field or our gradient vectors here. So that's that red portion here. And then I'm showing our gradient field here with the green arrows here. Let's just go up and look at that here. That's that green portion here that's got that algebraic function here. Again, looking at it, pointing at our gradient path here. It's sort of a little hard to see. The smaller arrows here, and that's where we would have the less and less material or labor input here. Smaller arrows here, and they increase. They get bigger and bigger, those arrows, as we increase our labor output. But it's at that specific point here, at where we have we're going to have both material and labor here at very minimal input at the initial point here. And then the arrows really aren't, they're almost getting to nothing here. Or you can see them very small here once you get out where you've got very large inputs of material and labor here into the production function. They're really hard to see here. Okay, so that was our red and green portion here. Now, I could have also put the blue, let's look at that blue portion. The blue portion up here, that second sum of our products here, that I've got to show over here because I'm showing those blue arrows over here. They would be covered up by those red arrows. They overlap each other. So I'm showing them separately here. So the blue arrows, you can see on that part of our function, let's just go look at it, that part here, that second part of our sums here, you can see here when we start out with our initial outputs, we got a really big blue arrow here. That's the gradient path, and it's pointing, it happens to be right on our gradient path maximum output minimum cost here. And you can see as we increase our, in this case, material inputs here, those arrows get smaller and smaller. But nonetheless, they're sitting here at some output where we got our initial outputs here for material and labor. Just to point out. So the idea is here, and then green arrows, I'm showing the same thing as we had before over on the other side here. We're to a lesser and lesser degree here. That green arrow is that function up over here. Our third part to our sum of products here on our determinant here. But nonetheless, you can see they do have a direction. Everything is pointing in a direction here. It's pointing in a direction of our maximum output here, or minimum cost, as you want to look at it. And again, the green arrows, you can see are really big over here, lesser, little smaller over here. But it gives you, the idea is to use these to understand, rather than just look at some mathematical function here that's really looking at some second partial derivatives of some function. It's good to graph it out and plot it out and see what's going on here. The only point is here, as you increase our outputs here and move at our greater and greater increases here in our output here, the arrows are going to get smaller and smaller here. These arrows here are only representing those initial outputs, but they do point, they give you direction here and really volume or changes we're looking at. We're looking at in change of slopes here. Okay, so let's move down over here. Okay, I'm showing it here in blue. The same thing. This is our determinant, that three-part sum of products determinant. The green or the bluish green here, that's that function graphed out here. But now, what I've done here is I've taken the red, the blue, and the yellow portions, that three-part function here, and I've just added everything together here. So what it does here, it just turns into a vector field here, a gradient field here, pointing in the direction of the greatest increases or minimum cost here. It's pointing in a direction. It gives you, we're going to look at it in terms of volume here just to understand what we're talking about. So when we have up here is where we had those initial outputs, and then as we increase our initial inputs of material, and as we increase those inputs of material and labor, it follows around this gradient path here. So we got some steep slope here, and then lesser and lesser degrees. And that's what we're talking about. These arrows here, these big arrows here, they're really representing our output, our initial outputs here, not the output here. The output here, when we move down along our gradient path here, these blue spheres here, this is where the arrows get really, really small. And they're pointing in the direction of the greatest input or greatest output here, but you're getting less and less change, or less and less effect here for your material and inputs for this production function here. So this really, again, gives you an idea, gives you the points, paths. It's a little misleading here because you think that at this point here, you're really getting a lot of output. No, this big arrow here and pointing in a direction really represents this initial inputs over here. And these little arrows as you move down here, that represents your outputs here because you're moving down along your graph here. So you're looking at the change in slope, the change in volume, and the direction. And what we mean by the change in volume, if we would have looked at that 3x3 matrix here and did a geometric solution at those, let's just look at it. It really turns into a parallelepiped here, a parallelogram here represented by those three vectors or those 3x3 matrix here for our material and labor inputs here. And what they do is they just expand it into the parallelepiped, and that's a whole different subject. But nonetheless, when we have those initial inputs, our volume is very big, and as we move down our gradient path here, our volume gets less and less here. So we're looking at this determinant here as a change in slope, and a determinant can relate to volume here. So you got big volumes over here when you have those initial outputs, and then as you move down your gradient path here, you get lesser and lesser volumes here. Okay, so that's, if you looked at it just in terms of volume here, just to understand those numbers. So if I move over here, I got three different points that I'd be looking at here. So we start our material and labor inputs here, and that's this point here, I think at 6 or 8 units of material and labor. Then I come up to 68 and 78 units here, that second point of material and labor, and then I come up here, I think I had 170 units of material, 190 units of labor, something like that. But nonetheless, you can see here where we started our initial inputs with a low part of our material and labor, we get a real steep slope, and as we increase our inputs, we get lesser and lesser slope here, represented by these green tangent surfaces here based on our inputs here. These are tangent planes essentially. And what this is really telling us, this determinant here, if we look at that initial output, I'm going to have a volume here, and that represented by the volume, the parallelepiped really is we're looking at 7.528 10 to the 6. So what would that be? 7,528,000, something like that. All right, so that's our initial input for material and labor, and then as we move down over here, this is the number that we were working with here for that for our example was 4.9 or 497,310 or something like that. So you can see jump from 7 million here down to 497,000 just looking at, so our slope is changing and our volume is changing, and the determinant is really based on volume here. And then if we got down to this last point here, we moved down 10 to the 5th, 168,700. That is what our greatest amount of material and labor input here. Okay, so the idea, as you can see, we have that steep slope here, large volume, 7 million something, and that's represented by the parallelepiped. Then we get that at intermediate point here, we get down to 497,000 from 7 million. So you can see based on volume and our change in slope. And then we got down from 497,000 down to 168,700. Okay, so that's just what we're talking about here, but we're going to expand on this determinant here, looking at it in terms of that three-part sum of products, just to get a little better visual understanding. So we'll continue on with that. Okay, now we'll expand on this determinant here, our sum of products, to get a little better understanding of what's going on here. And we'll look at it in terms of, and what we're going to do here with this three-part sum of products for a determinant, I'm just going to do a Taylor expansion against this product here, the sum of products. And I'll do it to the 8th degree. And really what we're talking about, we're taking the derivative here of this determinant multivariate solution here. And that would, if we do that 8 times, taking the derivative of the derivative of the derivative, you're going to get pages and pages of the solution based on that 8th degree Taylor expansion. Really what you're looking at by doing that, we're really looking at the change in slope or the curvature of our determinant here. And what we're trying to do is just trying to linearize that determinant to get a little better understanding. So what I've done here, looking at my plot here, this is the 8th derivative here, or the 8th derivative based on a Taylor expansion of our determinant here. And let's understand it. So we've got the blue portion shown here, then our red portion here, second portion here to our sum of products is shown here, and then the green is shown here. And what we've done here is we've taken that Taylor expansion, just to understand it. So I've got the blue here, here's our blue here. And what we really want to look at is with this 3 parts here, we want to follow, we're looking at a seam here. And this seam here is really our gradient path. That's the path here of our maximum output for our inputs of material and labor here for a production function. So here's our blue portion, that's represented here by our determinant here. And you can see where it's falling on our seam here, and then it wings down over here. So the key is here, when we've done this Taylor expansion, I've flattened it out here. I linearized this function in the area here of our gradient path. And what it's doing here, you can see where it wings out here. This is where you're getting a real steep increase, changes here in slope when it wings out. What's up here, you're having a 0 slope essentially, or 0 change here. And then over here, where it wings out is you're going to have maybe some greater input for material and lesser for labor and so forth. Some combinations causing you a fall off here. Okay, so this is the blue one here, and then the red one here. You can see a little intersection here, and then it's lying under our blue section here, blue graph here. And really it's probably falling under that seam here. I just can't look at it right now though, with the way it's plotted out. And then the green one, that's the green one was this portion here, that part of our function here to the 8th, all of it's to the 8th derivative. So the green here, again, you can see where it's intersecting here with our gradient path, where it's falling. It's falling a little under our red here, and then it's seaming up with our blue here. So you can see, and this is where you're at when we have these greatest increases here in material and labor. You can see it's dropping off and you're having some curvature here. This is where you're having really a great change in volume or slope as we'd be looking at it. Okay, so it's nice to take that function and try to linearize it to get the idea, or take our determinant, try to linearize and see what's going on around the area that we'd be very interested in, this our gradient path. And then if we move down here, you can see the same thing. Now I'm looking, this yellow point here, that's our initial input here, just to make a point of that. Up above, same thing. But we're moving our gradient path in this direction here. So we've linearized it in this area here. You can see the red. A little hard to see the wing out here, but then you can see the green showing here, and it's where you have that intersection, and then here's the blue. And you can also see, it's kind of interesting, it wings up over in this area. This is where we couldn't quite linearize it. And then you can see where it drops off here in those wings here. Here's our green portion of our sum of products, and then here's our blue portion. But this is the case here where you're going to have some odd combination of material and labor. We're interested in flattening it out here, and that's what we've done here. So you can see where the intersection is. So let's go up over here. Okay, so just looking at the same function here, just looking into them, really a side view here, and just in relative to our production function here, and actually looking at this production function, this is where's our initial input here, and then we looked at those 2 other points where we move up, and really we have a change in slope. We have a great change in slope here, initial inputs, that is we're getting greater outputs here based on our labor and material inputs, and then it kind of flattens out. But what we're doing here with our determinant here, you can see what's going on here. This is our initial point here, and we're looking really at the change of slope, but we run that 8th degree expansion against that determinant function here. So you can see this is our we flattened it out in this area for both our blue portion, red portion, and green portion here. But they're moving off, and then as we increase our outputs here, they drop off. And that really represents this area here. It kind of looks the same here, but you have to watch the symmetry here is just, or the direction is the opposite. Here's where we're getting our increases here in our material and labor for our determinant here, and this is for increasing in this direction here for our production function. And then if we look at the other side, same thing. Here's our initial point here, and this is where we're increasing our material and labor inputs. Again, you get a view from the side here. So here's our blue portion, here's our red and green here, and you can see where the seam is here. So kind of interesting just by plotting it out and getting a better understanding of what we're talking about here for the determinant here, rather than just a single number or a block of numbers or just looking at a multivariate solution here. We actually put that to being able to plot it out here. Okay, so if we move down over here, again, now this is where I put that gradient path in for those 3 different points. I just laid it right in over, remember that 3-part solution that I initially looked at here. I just laid it in, and you can see it's following right on the seam here, where we have the intersection of our red portion, our blue portion, and our green portion here of our sum of products of our determinant. And you can see here's where it's dropping off here, where we've got those curvatures here. That's where you're going to have some larger increases in material and virtually nothing of labor or something like that, or vice versa here. But we're able to linearize it here, and that's our gradient path here. And then if we look at the side view here, again looking at it here, so here's where we initial input, mid-range input here, material and labor, and then we got to this is where we have that greatest increase in our greatest amount of material and labor, and this is where we're going to actually we're going to go out at a loss here on our production function based revenue minus cost. Here we have a loss, and this is where we're just happens to beat out a determinant here. This is where it's no longer linearized. We're getting really a great change here in slope or a reduction here in volume. Okay, so let's just look at it as a side view. So we're able to look at again, look at the gradient path here where it intersects on our seams. All right, and if I go and I tie that into our gradient determinant here, remember we had that blue one here? And again, this is our gradient vectors or a gradient path here. I got the green, the red here, and then the blue. And they're all pointing in the direction of that gradient path that we're looking at here. Different size arrows, and where we had initial inputs, we had the greatest amount here. Just tying them in here, and you can go back up here and look at the same thing here. Just trying to tie in that determinant here. In this blue area, this is just taking the determinant itself, that multivariate solution, and just plotting it here. Whereas what's done here is I've taken the determinant, that 3-part solution here, and expanded it to the 8th derivative here of the determinant function here. So that's why we're looking at it. So you can make a comparison here just by looking at it in those terms. Okay, so we'll go down and we'll continue with this. Okay, now we'll expand on this determinant solution, that 3-part solution here, 1, 2, and 3 here. So let's go and let's look at it over here. Now, this is where I plotted the determinant solution, and it was based on that Taylor expansion, the 8th degree of the 8th derivative here of our function. But I've added all of our 3 parts all together, just adding everything together, the 3 parts. And then I've done this Taylor expansion just based on adding everything together at some points here. So what we're looking at it is this here. I've got the Taylor expansion itself here with the determinant here. I've got plotted out here in 3D here based on the expansion. It's adding everything together, the change in slope, 1, 2, and 3, the 3-part solution, everything added together here. So it's got this function here. So you can see where you got your flat surface over here, where you've linearized along your gradient path. This red dots here, or spheres here, are gradient path, and that's where I have an initial input. And then I've laid on top at the gradient field, or the vector field here, the gradients, where you can see they're increasing, how they fall on to our determinant here when we add all those 3 parts together here. Here's my green ones here. You can see where the greatest increases here, and I've linearized them here. Here's the increasing here. And then if I move over here and just look at it a side view here, this is initial point here, and then as we increase our inputs in material and labor here, following this gradient path, but it falls off here. This is the determinant here. That was the 8th degree determinant, all added together, parts 1, 2, and 3. Anyway, it gives you an idea of where you got the change in slope, where our gradient, along our gradient path here, we've linearized it here by doing the 8th degree expansion on our determinant. Okay, and if we go down over here, just looking at what we had graphed out before here, though, plot the determinant, the three parts separately here. Again, parts blue, 1, 2, here's red, 3 green, but I put on those gradient, or the gradient vectors here, the gradient field here. You can just see the relationship here. You get real big input here for the green, red portion here, and it tails off here, and then the green, same thing. Start out some input here, and that's at your initial inputs here for material and labor. And then you can see they're pointing, everything's pointing in here to our gradient field, our gradient path here, where the increases here. And you can see again where they're tailing off here, where we have your great changes in slope. And just looking at the side view here, again, our initial point here, and then we're moving down here. And you know, with our this is the three parts are separately here, the blue, green, and red parts here. And then you get at some point here where you get that, you got an inflection point. You're looking at a loss at this point. This is where you're going to have some real big slopes here. Okay, it gives you that view. And then if we just go over here and just to summarize it again. Now, if going back to our three-part solution here, the three parts, if I just didn't take any determinant, or any, just taking that determinant as I mentioned before without any expansion, we're going to get this surface shown here in that bluish green surface here, and then there's our gradient path here. Everything, there's no expansion, it's just taking the function itself here, adding everything together, 1, 2, and 3, and just plotting that out, and then we get our gradient path here. That's plotted against that function too here, and then you just look at the change in slope. I put some tangent lines in here just to get an understanding where you got a real steep slope here, initial inputs for material and labor, and then they level off in both cases. And then just finally going at looking at a determinant, the rate of change here. So we have our initial input here, and at that point we got these real large 3D arrows here. That's where we're going to have a large change in volume here for our determinant. But as we move down or increase our inputs here in material and labor, this is where our determinant, we're going to get smaller and smaller volume changes, or changes here in our slope becomes less and less here if we follow along that determinant path. So here we're getting showing our gradient essentially here, this vector field, a change of volume here, and it also shows our direction here following along that gradient path here. Okay, so that'll summarize our discussion here on the determinants.